Good morning, pre-calc. So here's your do now. I got a sinusoid graph there. What's the amplitude? What's the period? Hit pause till you got your answers figured out. I'll just hang out. Okay, well, first of all, the amplitude. So the amplitude is measured from the midline up to the maximum to the top of the hill, or from the midline down to the bottom of the valley. So the midline is right across the x-axis. So how far up does the hilltop go? It's not actually labeled on there, but it's right between the 2 and the 4. So 3. Amplitude is 3. Period. Number 2. Period. Period is the length of one complete cycle. And so my little green graph walker there marking the beginning. You could start at lots of different places, but if we start at the y-axis at 0, going sideways, then we're right at the midline on our way uphill. And so we just need to find out when is the next time that we will come back to that same spot. And that would be at pi. So the horizontal distance across the graph, that's the period, pi. And so I've traced several cycles of this repeating pattern in different colors. So the green pattern, you go from the midline up to the maximum, down past the middle to the minimum, and then back up, hit the midline on your way uphill right there. That's at pi. Red would be what the next cycle looks like. That also has a length of pi. It's just the next pi over on the graph. The purple one, same story. Also, the purple part has a length of pi, starting at 2 pi and ending at 3 pi. So it's a difference of 1 pi. So any of those would illustrate the period. Today we're going to look at graphing sinusoids. So we're going to be heading towards this learning target. You'll be able to transform the graph of sinusoids using period and phase shift. We're actually going to put a hold on period. We'll get to that next time. So we're just only looking at phase shift today. Let's go ahead and put period on hold. We'll come to that later. So we have transformations, which we've learned about in the past that apply to all functions. We've already looked at the vertical transformations, and so today we're going to start looking at the horizontal translation. So this horizontal translation is actually the only one that we will look at today. And like amplitude, horizontal phase, which had a special name instead of a vertical stretch or vertical shrink, we call it amplitude. So there's another special name for this translation as it applies to sinusoid. So horizontal translation, we just take the graph, slide it left or right across the graph, across the x-axis, like it's a special name for sinusoids. It works exactly the same, but it's called phase shift. And that's what we'll be looking at today. So we already learned about, it's inside the parentheses. That's one of the ways we recognize that it is horizontal. So it's going to be inside those parentheses after the word sine or cosine, after that function name. And then there'll be a theta or an x or whatever variable we're using. If after that variable, theta or x or t or whatever, it says plus a number or minus a number, that's going to move the graph either left or right. It goes backwards from the way we think. So if it says minus some number, it's actually moving the graph to the right. And if it says plus some number, it's actually moving the graph to the left. And so the effect on the coordinates is the opposite sign of what the function indicates, because it's backwards. Okay, so we have these 5 key points for the graph of sine. Look at the 5 key points of the graph of cosine. We have seen those before. I explained those in the previous video, so if you want, go back and watch that again. Important thing to, just remember, sine begins, our description begins from the midline, going up to the maximum first, and then down to the minimum before it returns at one full period at the midline. Cosine starts at a different place. It follows the same pattern, but starts from the maximum. So at time 0 or angle 0, we're up at the maximum, and then the graph goes down to the middle, down to the bottoms out at the minimum, comes back up midline, and then returns to the maximum at one full period. Same locations, minimum, maximum, midline, is just where we start from. That's the only real difference between the sine and cosine. So we had some vocabulary before. We've already talked about midline, which is not actually part of the graph. It is not a thing that we need on the graph, but super helpful for both drawing, visualizing, understanding what's going on with the graph. And so that forms the middle, halfway between the maximum and the minimum. Period, we talked about in the do now, is the horizontal length, the one full cycle of that wave. It's the building block for our infinitely repeating pattern. Amplitude gives us the height measured from the midline up to the maximum, or from the midline down to the minimum, which is the same. The vertical translations we already talked about last time. We take that graph and shift the midline up or down. So today, we got period. We're not going to deal with period today. There is a transformation, which we'll see next time, that changes the period. But for today, since there will not be any transformation to the period is always going to be 2 pi. Right? And the place that you would see, and you won't see it today, but the place you would see in the equation, the transformation which affects the period, is this k, which is being multiplied onto the theta. It's not always going to be a theta, but whatever variable we're using. If there's some number, k, that's getting multiplied onto the theta inside the parentheses of the function, that's going to change the period. So as long as we don't see that, there's no number in there being multiplied on the theta, that means the period is 2 pi. Okay, so phase shift. Here's the new piece we're looking at today. So phase shift, as I mentioned, is a special name that's applied to the horizontal shift of our wave-shaped graph. And it works exactly the same as we've seen before. Inside the parentheses, you're going to see theta minus some number. We're going to call it c. If you got minus some number c, it's going to shift the starting point of our repeating pattern to the right by c spaces. And on the other hand, if you see inside the parentheses theta plus c, that is going to shift the starting point of our repeating pattern to the left by c spaces. So let's do some examples. So I got y equals cosine of theta plus pi over 2. Before we start graphing, let's identify some important informations we'll need to, some important pieces of information we're going to need in order to draw the graph correctly. What's the amplitude? It's 1. What's the period? Well, there's an invisible 1 being multiplied onto the theta, and as long as we have that coefficient of 1, that means the period is not altered, it has not been transformed, so it's 2 pi. I do need to know what the period is so I can actually draw this thing correctly, because that's going to be the end of my repeating pattern. What's the phase shift? All right, well, phase shift right here, this is the new part. Inside those parentheses, I got theta plus pi over 2. Plus is going to move my graph to the left. So the phase shift is left pi over 2, or we could say negative pi over 2. So for actually understanding, it probably is better to say left. But if you were to answer a question like this on WAMAP, you would need to use minus pi over 2, because it will be moving in the negative direction across the x-axis. Okay, so before I start drawing things on the graph, I'm going to put some guidelines on my graph. So the amplitude, I need the midline first. There was no vertical transformation, so my midline stays as the x-axis. The amplitude is 1. That's what I'm going to use to find both the maximum and the minimum. So from that midline, I need to go up 1 space. Here's the maximum. And from that midline, I need to go down 1 space. That is the minimum. I'll go ahead and label these. There's the max. There's the min. This one is the midline. All right. So the graph in this case is a cosine graph. Cosine starts at the multiple choice. Maximum, middle, or minimum? Cosine starts at the maximum. Nice job. Okay, so on the y-axis is where I'm going to start from. That cosine graph needs to start at the maximum up at the top, so that's going to be where my guideline is for the maximum. But before I draw that on the graph, there's a phase shift. So my starting point, instead of being on the y-axis, I need to shift to the left by pi over 2. So here's where I'm going to start drawing my cosine graph from. So instead of starting at the y-axis, I got to shift left by pi over 2 spaces. And then I like to do my 5 key points. I like to do the beginning one first and then the ending one. And so the period is 2 pi. So I can use the period to find where this cycle, where this chunk of my repeating pattern, where does it end? It's going to end 2 pi later. Not necessarily at 2 pi, but 2 pi later. So a couple of ways you could do it. One thing is you could just count sideways across the graph until you get to 2 pi spaces, which is kind of, some people do that. You got to pay attention to how the graph is marked. So in this case, it's marked every pi over 2 or every half pi. So I would need 4 graph lines to make 2 pi. 1, 2, 3, 4. So I'm just going to end right here. Another way you could do it is you could go to 2 pi. You could find 2 pi on the x-axis and then apply the phase shift of moving left by pi over 2. So you'd say, all right, well, here's where I'm supposed to end. Normally, I got to back up by pi over 2, go left pi over 2. Another way you could do it is you could just take the starting point, which was negative pi over 2, and you could add negative pi over 2 plus 2 pi, which is the period, and that will tell you the ending value. But then you have to add with fractions and pi, and people don't like that. And you totally can. Any of those approaches is going to give you the same ending point. Okay, so I got my start and I got my end. They're both at the maximum. I know at halfway through the period, so halfway from the start to the finish, cosine graph will be at the minimum. So halfway from the first dot to the second dot, sideways halfway, is going to be at the pi over 2 mark. Whoops, don't want to scribble. And it'll be at the minimum. So I can go ahead and put a dot at the minimum right there. Halfway between the first 2 dots, that'll be the quarter way through the period. It'll be at the midpoint. And so halfway from the start to from the maximum point to the minimum point is going to be at the midline. And then I can find my 3/4 point through the period, which will be halfway between the minimum and the max, sideways halfway between the minimum and the maximum. So that's right here at pi. So there are my 5 key points. Smooth curve. And then that pattern repeats infinitely. So if I'm drawing this by hand, I'm going to need to put some more points on here and plot some more wave cycles. So if I go forward towards the right, I'm at the maximum. And if I look back at what just happened, every graph paper line, I was at the next key point, which was convenient. Sometimes the graphs are not marked. The period doesn't mark up with the graph paper lines. In this case, they did. So I'm at the maximum at 3 pi over 2. The next graph paper line will be at the midline. And if there were another graph paper line after that, I would be at the minimum. And then if there was more space I could draw, I could keep going. Okay, what about towards the left? I just do that same pattern, but going backwards. So if at negative pi over 2, I am at the maximum. Backwards by 1 graph paper line will be at the midline. Backwards 1 more is at the minimum. Backwards 1 more is at the midline. Backwards 1 more. I can make that fit. It's going to be back to the maximum. So you can see that same wave chunk repeating in purple, and then repeating again in blue, and then repeating again in red, and then repeating again and again and again and again. So the up and down motion of the graph does not ever change. It's just where I start drawing from that's affected by the phase shift. Hey, so an alternative way of thinking about this phase shift is, you can use one of my awesome analogies. Think about the Ferris wheel rider. This equation says we're going to take our theta value and advance plus. We're going to, the analogy, we don't actually do the opposite. We're going to advance by pi over 2. So cosine starts at the maximum, and then we're going to advance by pi over 2. Pi over 2 is 1/4 rotation. It's like 90 degrees, right? A quarter of a circle. So cosine graph would start at the top. So if we just think about from the perspective of the analogy, that's like our graph walker starting at the top, the maximum height of the Ferris wheel. But instead, we're going to advance pi over 2 radians, or a quarter circle, 90 degrees. So the graph walker is going to be at the midline, and the Ferris wheel still rotates counterclockwise. So we're going to start at the midline, and this graph walker's first move will be going down around the circle. Okay, so that's what it would look like if we were to begin our graph from the y-axis. At the y-axis on this graph, we're going to start at the midline going down. So let's see what just happened. On the graph we just drew, if we were to begin drawing from the y-axis, we're at the midline, and the graph traces down first. From the midline goes down to the minimum, okay, which is exactly the same thing that our little graph walker does. And if we're drawing it this way, then we're going to think about period differently, because if we're starting from the y-axis at 0, then we're going to want to end 2 pi later, so that'd be the full period. So our cycle is going to be all wonky. We're starting at the midline, down to the minimum, up to the midline, past the midline to the maximum, and one full period is going to end at 2 pi. I need to be at the exact same place I just started. So if I started at the midline going down, I need to end 2 pi at the midline going down. And that's what I've got. It's the exact same graph, totally different way of thinking about that phase shift. Okay, example number 2. Y equals sine of theta minus 3 pi over 2. So let's do the same series of questions. What's the amplitude? It is 1. There's no amplitude number out there. What's the period? Since there is not a transformation being multiplied onto that theta, means the period is still 2 pi. And the phase shift right there, minus, it says in the equation, minus 3 pi over 2. And so that is going to give me a phase shift to the right by 3 pi over 2. Don't forget the 3. And if we're entering this into a WAMAP question that asks us what's the phase shift, we would just say positive 3 pi over 2, or just 3 pi over 2 would mean the same thing. Okay, so we're going to get some guidelines on this graph. So midline is going to be right down the x-axis. The amplitude is 1, so my maximum is going to be up 1, and minimum is going to be down 1. Missed that one a little bit. Okay, and then when I start drawing my graph, it's a sine graph. Sine starts at the midline and goes up first. So normally I would start at the y-axis. So I'm looking for the midline at the y-axis, except there's a phase shift. So instead of beginning at the y-axis, I'm going to shift to the right by 3 pi over 2. There is my first point. Okay, so I'm going to draw my waveform starting at the midline and then going up to the maximum first. So I just need to shift everything to the right by 3 pi over 2. Okay, so where's it going to end? One way to get the end, same 3 methods we talked about last time, but so I know that normally the end would be at 2 pi, which is right here. So I just need to shift my ending point right by 3 pi over 2. So there's 1 pi over 2, 2 pi over 2, 3 pi over 2. So I'm going to end right here. Or you could convert to fractions. 2 pi is the same as 4 pi over 2, and add 4 pi over 2 plus 3 pi over 2 to get 7 pi over 2 as is marked on the graph. Okay, so there's my start and my end. Halfway cross sideways, halfway through the period, I'll be at the midpoint again. At the 1/4 of the way through the period, I'll be at the maximum. The 3/4 point, I'm going to be at the minimum. And then I can connect my 5 key points. There's one waveform. If I continue to the right, next point is going to be at the maximum, and then I can fit that next point there at the midpoint, and it would keep going, but I'm out of graph. If I continue this to the left, the first point I have drawn on here is at the midline. The point before that would be at the minimum, and then before that would be at the midline, and before that at the maximum, and before that at the midline. And then if I keep going even further left, the point before that is going to be at the minimum, and then just enough room to guess where that one would be. I can only fit half of that waveform on there. Okay, so there's my graph. And again, we can understand this by using as a totally different approach to understanding the phase shift. We could think about one of those analogies. Let's use the little prince walking around the planet this time. So the little prince for sine is going to start in standard position over there at the midline. But we're going to shift the little prince backwards. So the equation says minus. They're going to back up the little prince by 3 pi over 2. 3 pi over 2, that is 3/4 of a circle. So I'm going to back them up 3/4 of a rotation. Okay, so here's my little ghost image of the little prince. Normally would start at 0 radians, but I'm going to back up by 3 pi over 2, which means the little prince will be standing up there at the maximum. And so this phase shift means if I start drawing my graph from the y-axis, I'm going to start at the maximum. And then the little prince still continues to go counterclockwise. Always go counterclockwise around the unit circle, but start at the maximum on the y-axis. And that's actually what we just drew. Okay, so depending on how you want to think about it, if you want to just draw the waveform and shift it minus in the equation is going to mean that we actually are shifting to the right. And so I drew my blue waveform shifted to the right by 3 pi over 2 spaces. Alternatively, you could say, look, the minus 3 pi over 2 actually means our little graph walker on the unit circle does minus 3 pi over 2, and then that's where we start our graph from at the y-axis. All right, example, another one, the last one here. Y equals 2 sine of theta minus pi. So amplitude is 2. The period is still going to be 2 pi. The coefficient on the theta is a 1. That means there's no transformation, so the period is 2 pi. And the phase shift right there is minus pi, and so that is to the right by pi spaces. Or if we're answering this onto a WAMAP question that says, what's the phase shift? We'd say positive pi or just pi. All right, let's get some guidelines on here. The midline has not changed. There's no vertical shift, so midline goes right down the x-axis. The amplitude is 2, and so I'm going to use that to get my maximum. Will be up 2 spaces from the midline, and the minimum will be 2 spaces down from the midline. Sine graph, this time sine starts from the midline. All right, so on the y-axis, I would be at the midline, and then there's a phase shift. I need to go to the right pi spaces, so I'm going to start my waveform at pi. The ending point of my waveform is going to be 1 full period later. The period is 2 pi. I could do mental math and say, hey, if I'm starting at pi, that's my starting point, I need to go to the right 2 pi to get the full period. Pi plus 2 pi is 3 pi. So there's a different approach. We can get the ending point. Going sideways, I got the 0 period and I got 1 full period. Halfway through the period, I'll be at the midline again. 1/4 of the way through the period, I'll be at the maximum. 3/4 of the way through the period, I'll be at the minimum. So there's one waveform. If I continue that pattern to the right, maximum, midline, and then it's going to go down, but I ran out of room. If I continue to the left, conveniently, this is every graph paper space. So backwards, it'll be at the minimum, and then the midline, and then the maximum, and then the midline. Before that, minimum, midline, maximum, midline. And before that, I didn't get about that much of it. Okay, so there's what my graph should look like. And alternatively, I could think about this phase shift using a Ferris wheel analogy. So the equation here says theta minus pi. So I'm going to take my graph walker on the Ferris wheel and back them up by pi. Pi is half a rotation, so it's going to go half a circle backwards. Sine normally starts on the 0 radians on the, when I'm looking at the graph, it's going to be on the right-hand side at the midline. So if I back up by pi, that's going to put me on the left-hand side at the midline, as illustrated by my lovely assistant, Green Graph Walker, a little ghost image where we were starting at 0 radians, but if we back up by pi, puts us on the other side of the circle halfway around over here at the 180 degree mark, or at pi on the unit circle. And then always proceed counterclockwise. That's the way the unit circle goes. So if I start from the midline, once I start drawing my graph at the y-axis, start at the midline and then go down, because the graph walker is always going to proceed counterclockwise. So start at the midline going down. And if I look at the graph I just drew, that is exactly what happened. From the y-axis, we started at the midline and went down first. And if we're thinking about the whole period, my colors are not matched up this way. So I would just say, well, look, I started at the midline going down. And so one complete wave cycle would be this half, kind of half loop with green, and then the first half loop of the blue that would be together as my one unit, and then that would repeat. I always thought that's weird to think about that, because it's like, but that's not actually what sine looks like. Sine doesn't go down first. So it does work, and people have different preferences. Whichever of those options works for you to get the phase shift on here correctly.